no idea if you can see clearly. So there are 4 levels of programmer that we prompt. So basically, this is a agent. This is a main prompt, but we do have the other like agent stuff. It's a bit complex, but the basic idea is, at a junior level, we just tell large language model the task or problem definition of the algorithm, and we don't give them any other technical details. So that's the junior level. And moving to intermediate, and in addition to the problem definition, we also offers like minimal technical information. For example, what the task is about, you may refer to where for this programming this certain problem. And going to the senior levels, and we show them extra examples of doing programming. For example, while programming PageRank, we may show them the some code, a program breadth search, etc. And to the expert level, we directly provide the pseudocode of the algorithm. So did this answer your question? Cool, thank you. Okay. Cool. Right. So good morning. It's a pleasure to be here. Thanks, Shipeng. Thanks, Alex, for having me here. And today, this is Longbin Live, basically. And I'm currently from the team of GraphScope, Tony Lab Alibaba. And today, I will going to introduce GOPT, which is a Graph Native Query Optimization Framework. So the first part, I will get through the motivation and overview the whole solution. We all know that all database systems use declarative query as input, although you previously talked about, declarative versus imperative. But, declarative language is still most widely adopted in all database systems. And they rely on an optimizer to derive an execution plan in order to run efficiently on the backend engine, right? So, undoubtedly, like optimizer is a most key performance impact factor in database systems, right? No matter it's a relational one or it's a graph one. So since the invention of SQL in 1970s, query optimization has become an important topic in the DB community. And we have, over the past decade, this is a very typical relational query optimization pipeline. First of all, a relational query will be converted or transformed into relational algebra representation. And then the representation will get optimized by any optimization framework optimizer using equivalent transformation rules on the relational algebra, right? This is a very typical optimization pipeline for a relational database. No, sorry. I think it's not working properly. But yeah, today I would like to ask, with all our dearest Graph fellow present here, I do want to ask everyone a question. Do Graph have such a unified optimization framework, a pipeline that everybody use? Right? There's no. There's no. There might be multiple reasons for this, but one primary reason that I consider, it's just my personal point of view, is unlike relational query, we have a uniform query language SQL and a unified representation called relational algebra. Like everybody can implement the same framework using the same input. But in Graph database, we already have a variety of Graph query language. For the most widely mentioned, we already have GrabName from Tinkerpop and Cypher from Neo4j. And more recently, there have been standardization efforts, seeing the fragmentation of this field, which result in two projects. One is called PGQ in 2023, and the other is GQL this year. It's a very new topic. But before this standardized query language being widely adopted in the community, they just add variations to this already fragmented field, right? And one potential pipeline for optimizing graph algorithm, the one that I called non-graph native, is to convert whatever type of graph query language into the relational algebra first. And then we can leverage any relational optimization technique to optimize graph queries. So this kind of pipeline is feasible, at least partially, in both theory and practice. However, such pipeline has obvious, downside. One of the downside is it experiences performance degradation. As my colleague gonna cover in later guard talk here. So, while converting into relational, for example, graph pattern matching gain neighbors, it will be converted into joint operations. It will suffer from performance degradation. And let alone, we have the other semantic differences. For example, like recursive, like yesterday, Professor Zhou talked, like PRQ, such kind of query can be very hardly expressed using relational operations alone. And to fill in this gap, we have worked in the past few years on this project of GOPT, which is called a Graph Native Optimization Framework. So it's designed and implemented for Graph natively. So in order to do that, we first introduced that unified representation, which contained some relational operations, as you can see, and also some graph primitives, including graph pattern matching, and path expansion, edge expansion, getting verses, etc. I think Professor Zhou from Peking University did cover this topic a bit yesterday, but he's from more like theoretical perspective, but we pay more attention to the engineering perspective. But basically, we have end up with a very similar idea. We need unified representation, just like relational algebra. And then, based on this representation, we can do the following optimization way in a very uniform pipeline. And hopefully, the representation can be designed and implemented to support as many as query language as possible. So including like Cypher, Tinkerpop, and later on, we're moving to support of GQL standard, of course. Right. And after the optimization has been done, we still have multiple different backend engine to support. So we define the final physical plane as a prototype in order to be integrated into different backend engines. So this is not only work for Graph database. See, we also prepare this for relational as well because of SQL PGQ, obviously. So moving to part two, I'm gonna overview several key techniques introduced in GOPT, which include the intermediate representation, the type inference technique, and a little bit like RBO and CBO. We consider this very simple query scenario, which describe the shopping activities among people and a little bit of their social and geographical relationship on these entities. And then this user query is simple. We just want to match a triangle pattern, where it contain one place vertex, and then we filter this pattern with a specific place name and group the matchings by name and select the top 10 results. Using Cypher queries, this query could be represented like this. It's straightforward. So first step, we convert this query into a relational, into this intermediate representation. As we can see, the whole matching phrases has been converted into these blocks enclosed with the match start and match end. This is a core, this is core matching context. And we also have this relational operators as well. Yeah, I'll rush a little bit, but we do have a paper, so you can scan and get the link. So here's after it's been converted, the first technique we apply is type inference. So unlike relational database that we have a name for each table, while writing graph queries, people often leave certain vertices or edges unspecified, the type unspecified. So this is quite normal. But this does not mean that every type assignment is valid according to the schema. Make sense? So we have this type assignments. This is valid according to the schema. And this is also another valid assignment. However, this assignment is invalid. Invalid means that you are not going to query any correct results from the database because, according to the schema, there's not edges connecting two places. So this end up with this unified assignment of labels or types. So we have, like for example, V1 and E3 being assigned with a single type, which we call it basic type, and E1 and V2 have two available types. We call it unit type, and this definition is what we refer to the PG schema that published last year. Okay. Yeah, and then just several very typical optimization. One is rule-based. Obviously, with this kind of thing, we can push. So here's the predicates on V3. We can push this selection operation into matching context. So basically, this is the idea. This is the pull, like filter to join. It's very similar to filter to join operations, right? And we also have cost-based optimization, and this is the paper that we introduced several key techniques, and one is the high-order statistics. So in addition to the counts of certain type of vertices or edges, we also consider frequency of small patterns, for example, like two whole paths or triangles. This high-order statistics that make it more accurate to estimate the cost. And we also have considered this worst-case optimal join operation. And this is a spanning and section operation. It's actually the result of worst-case optimal join. And here, I just want to show, the system architecture of GLPT, which include, upper-level clients, which we offer various SDKs for different language, different query language to plug in. And currently, we have supported Cypher and Gremlin and definitely Neo4j, GQL and SQL PGQ, what we target in the future. And we also have various pluggable API, for example, the metadata provider for different backend engine to connect and provide their metadata, for example, the schema and the statistics if available. And we can help people plug in their own heuristic rules for rule-based optimization. And then we have designed a plan converter to convert the protobuf plan into what's executable on the backend engine. And I'll just quickly show two integrations. One is to the Neo4j using Cypher as an input, and the other is a research project we have done recently. So we managed to optimize SQL PGQ on DuckDB. Just skip the technical detail and just show the results. So here is a very recent integration of GLPT in Neo4j. Using basically the LDBC graph. This is from LDBC benchmark, but we don't use most the LDBC queries, but rather rely on several curated query for demonstrating the key techniques specifically. As we can see that there are several techniques I've mentioned. Each can improve the query by a substantial margin. And using LSQB's queries, because it's specifically designed for pattern matching, the impact is even more. Like for example, QLS3, the plan after optimized by GLPT can complete in several hundred seconds, but Neo4j's native optimizer already run out of time. So they have all the same backend engine. So we're not using any very fast engine to tune this idea. So this is so due to the effectiveness of the optimization framework. And here is the result that we conducted on DuckDB. This paper has been submitted and accepted by SIGMOD 2025 next year. So yeah, it's a kind of like research oriented, but we're seeking to collaborate with Peter, hopefully, to make it work on DuckDB for engineering aspects. But this is a result. While compared to the original, the original plan generated by DuckDB is whatever told that non-graph native. It all converts to relational stuff. And GLPT on DuckDB do generate performance speed up of over 20 times. So it's 20 times faster than natively DuckDB's plan. And for the other queries like job queries, it's also 8 times faster. And notably, this kind of queries, they are specifically designed for relational. And we also tested several queries from business intelligence benchmark, and the performance speed up is more substantial compared to the interactive complex. Yeah, I want to especially thank our whole team from GraphScope for their support of the optimization framework to make it possible. And this special thanks goes to this developer of GLPT, Bingqing, Xiaoli, Yunkai, and Yufan. Thank you very much. Yeah, and if you want to try GLPT, you can scan the code on the left part. And if you want to collaborate or contact us, you can scan the right code. It's a WeChat channel. Thank you. Any questions? Sure, Alex.
It's working. Yeah. Have you sold it to Neo4j yet?
They are too busy with GrabRack stuff.
So no, my serious question was actually about your adaptive schema plugin and your approach to use of schema. So let's imagine that you have no schema, right? You just start with raw Neo4j. There's nothing at all, right? Do you build up schema during incrementally during the course of actually carrying out query planning? And if you don't, whatever the answer is to that, my second question is, you can basically plug in some level of schema from the side if it exists. Yeah. Could you sort of give an indication of how sophisticated that schema can be? What is it? What's the information content that I can give you through that pluggable interface?
Okay, that's great question. So Alex asking about our handling of schema from different platforms, for example, Neo4j. And here's the answer. We actually recently rely on the APOC procedure provided by Neo4j to obtain the schema. But the original APOC procedure given by Neo4j, is based on sampling, and which may miss information. So we periodically, scan the whole database in order to obtain the correct one. But this is mainly, the schema is mainly for so for type inference, as you can imagine. Even there's zero schema, we can still work. But the effect may be less than what we have the whole information. And about the format of the schema, recently we don't have many. For example, we don't refer to what you have been instructed on PG schema, sort of. Basically, we just maintain what type of vertices are and their counts, basically, and what type of edges.
But presumably, the more that was actually injected through schema, the more sophisticated this could be. Yes.
Primary key, for example.
So there's quite a lot that you could do.
And many-to-many relationship are another important statistics. And we have another research paper ongoing, leveraging these statistics for generating. Remember that we can compute like two-hop path.
Yeah.
But if we know that a certain path is many to one, then we can extend it to three-hop without adding any cost to it.
You're right. Yeah. So if you had cardinality information as well as key information in the schema, then you could take advantage of all of these kinds of things.
Yeah. We're definitely considering that. Yes.
Cool.
And it's we built upon Calcite, so that already have very good foundations of accepting different plugin rules, etc. Yes.
Thank you.
Cheers.
Any more questions?
Thanks for the great talk. I have a couple of questions. So the first is you use the schema graph, as you and Alistair just talked about. Use the schema graph to refine the choreograph. So do you just map or try to match the choreograph onto the schema graph first before doing the actual choreo planning?
Yep. It is. So for type inference, and you look into the type and try to see. So basically, it's a breadth of search, but we do cut it off for efficiency consideration.
Okay, so when there are multiple possibilities, you just do them in parallel.
Union them. It is.
Okay.
Yeah.
Okay, great. Okay, my second question is, I see that your GOpt, it performs much better than Neo4j's native optimizer. So what causes this intuitively? Is your plan space larger, or do you choose a more close to optimal plan in the same plan space?
You can show, I also show you the optimized time. So actually our optimization time is faster than Neo4j's native optimizer. I have no idea what secret trick of Neo4j's optimizer, but we do develop a lot to improve the efficiency of the optimizer itself. Yeah, but mainly the searching space is huge if you want to get the optimal. But luckily we don't necessarily need the most optimal, because among all the plans that we generated, they are not necessarily the most optimal one.
Yeah, sure. I'm just trying to get an idea of your plan space compared with Neo4j's plan space. So are they the same, or do you have a larger plan space which leads to a better plan, or are you looking into the same plan space, just that you're able to get the more optimal plan in that same plan space?
Cool. Honestly, I'm not sure about Neo4j, but we do have a theoretical analysis of a SQL PGQ in that paper. For Neo4j, I'm not sure, because I am not reading Neo4j's code. This is a result, but I'm not sure about the searching space. But for SQL PGQ, because you can see, the graph part, we have vertices and edges, rather than join two vertex table and edge tables, and you do have a reduced search space, basically.
Okay, thank you. So A last question.
Sure.
So Neo4j and DuckDB, you have integrated GOpt into these two systems somehow, and they have different physical operators, but
Yeah.
you use the same logical plans and then translate into their physical plans, right?
Yeah.
Okay,
Yes,
great.
that's right.
Okay, thank you.
Thank you.